Hi everyone. So today in this lecture you are going to understand the definition of poles and residues. So before going to poles and residue, we should know what is Lorentz series. Lorentz series is nothing but sum of an z minus a whole power n plus negative value a minus n z minus a whole power minus n. We denote this positive and negative power of z minus a as one part of analytic and the other part is nothing but principal. This is very important to understand the definition of pole and residue. First part, the positive one, is the analytical part, and the second negative power of z minus a is nothing but the principal part. So if the principal part of the function f of z, that means a negative power, right? The principal part of f of z consists of finite number of terms, then we say that z is equal to a is a pole of order n. The principal part consists of finite number of terms. Then we say that z is equal to a is a pole of order n. When z is equal to a, the principal part will be a singularity. Singularity is nothing but the function doesn't be an analytic there. Yes? Pole of order 1. Pole of order 1, we simply call it as a simple pole. The next point is, if the principal part of the function consists of infinite number of terms. If it is finite, then we call it as a pole. If it is infinite, then we call it as essential singularity. Singularity is nothing but a function f of z fails to be analytic at z is equal to a. The function fails to be analytic at z is equal to a. That's nothing but singularity. So the next point, if the principal part of the Lorentz series f of z is completely absent, that means you don't have any negative part in the series, then f of z is said to be removable singularity. So remember, finite is pole, infinite essential singularity. The second term, that is a principal part, is 0, then we call it as a removable singularity. So coming to the definition of residue, please go back to the same principal part of Lorentz series, where here instead of n1, okay, the coefficient of 1 by z minus a, that is the coefficient of a minus 1, when n is 1, right? The principal part, the coefficient of 1 by z minus a, that is a minus 1 in the principal part of the expansion of f of z, is nothing but the residue of the given point at z is equal to e. So let us take a small example to understand pole. Pole is nothing but it's a principal part of the Lorentz series whose value is finite at z is equal to e, right? So what you have to do, you have to check the denominator of the function. So what is the denominator we have? One is z minus 1, one is z plus 1. What happens when I replace z by 1? It becomes 0. That means a function is singularity. That means a function is not analytic. So when does this happen? When I take z is equal to 1. What is the power we have? The power is 1. So this is pole of order 1. Z is equal to 1 is a pole of order 1. That means when z is 1, this completely terminates to 0. That means f of z is not analytic. That point we will use the concept of pole. Now you take z when this term can be 0, when z is equal to minus 1. So what is the power we have? Power is 2. So z is equal to 2 is the, z is equal to minus 1 is a pole of order 2. So you should always keep in mind, when you substitute z by any value, the term becomes infinite, 1 by 0 infinite, right? So in that case, the function becomes singularity. Singularity is nothing but the function is not analytic. It fails to be analytic at the point. What are those points when z is 1 and z is minus 1? Depends on the power, you can say it is of order 1 and order 2. So consider one more example to identify the pole. Okay. Check the denominator. So one is z square, one is z plus 1. When these two terms tends to 0, when this two terms tends to 0, e power z by this 0 will terminate to infinity. So the function will not be analytic at that point. So when this can be 0, when you take z is equal to 0. So z is equal to 0 is a pole of order. See, the power of z is 2. So it's a pole of order 2. Z plus 1. So when I can expect the z plus 1 tends to 0, by which the function fails to be analytic. So what point is that? When z is equal to minus 1, this function will not be analytic. So this is a pole of order 1. Why we say it is a pole of order 1? Because whose power of the expression is 1. So consider this next example where it is quite different compared to others. So you should always remember our Lorentz series has denominator z minus a. So you should take the denominator term and try to express it in that way. Okay, only then you can identify the pole. So I can write z square. Instead of 1, I can write it as minus of I square. So what is I square is minus 1, minus of minus will become plus 1. Okay. So what will be the value of z now? So what should be the value of z? So the value of z, when I put it as the value of z square will be I square, right? So that means when z is equal to plus or minus I, these two values will make z square plus 1 to 0. So it's of order 2. Similarly, 4z square minus 1. So 4z square minus 1 can also be written as 2z the whole square minus 1 square equated to 0. You'll be able to identify which z value makes the term 0. So 2z square is equal to 1, right? So you can also express this as 2z is equal to plus or minus 1, or z is equal to plus or minus 1 by 2. So when you put plus 1 by 2 or minus 1 by 2, the term 4z square minus 1 will tend to 0. So what is a pole? It's a pole of order 1. Here the power was 2, so it was pole of order 2 pole, and here the power is 1, so pole of order 1. So consider an example for residue. So please remember the definition. Residue is nothing but it is a coefficient of 1 by z minus a term in the principal part of the expansion of f of z at z is equal to e. So keeping that in mind, and we know the expansion of cos, okay, all those concepts we are going to apply. So 1 by z power 5, expansion of cos, so it is 1 minus z square by 2 factorial, z power 4 by 4 factorial, odd power, even powers with alternate sign, 6 factorial, and goes on. Multiply that 1 by z inside. So by doing so we get 1 by z power 5 minus 1 by 2 factorial into 1 by z cube plus 1 by 4 factorial into 1 by z, because power of 4 and power of y, 1 power of z will be retained. Here the power of 6 is greater and power of 5 is less, so we have z by 6 factorial and so on. So we are supposed to concentrate on coefficient of 1 by z minus a. So you can see everything is z, so you can write this as z minus 0 power 5 minus 1 by 2 factorial, z minus 0 the whole cube plus 1 by 4 factorial, 1 by z minus 0 whole power 1, and goes on. So the residue lies with the coefficient of 1 by z minus 0. So this will not be considered, this will not be considered, the power of 1 will be considered. So 1 by z minus a. So the coefficient of 1 by z minus a is 1 by 4 factorial at z is equal to 0. The value of a is 0, right? So the given function whose residue is 1 by 24. So once we understand the definition of poles and residue, the next comes residue theorem. So if f of z is analytic in a closed curve C, except at few points, the singular points, as I said singular points, at that point the function will not be analytic. Leaving these few points, we are going to find the function analytic. Then we need to prove integral over a closed curve C, f of z dz is equal to 2 pi I into sum of residues. So this is very important theorem. So the statement is function has to be analytic inside and on except at few singular points. We are not worried about the few singular point. Then the theorem says that integral C f of z dz will be equal to 2 pi I into sum of all the residues. So keeping these concepts, we can move ahead in our next lecture where the problems of residues and other natures of singular, essential singular will be discussed. So kindly check into the next video. Thanks for watching.